Now, without further ado, let's get into this workshop. First things first, I want to explain what we mean when we talk about Arduino because it can refer to multiple different things. So according to the Arduino website, Arduino is an open source electronics platform based on easy to use hardware and software. It's intended for anyone making interactive projects. Arduino is actually the name of an open source hardware and software company, which has designed numerous circuit boards, such as the one pictured here under the quote. And when we talk about Arduino during this workshop, we are mainly going to be referring to this specific circuit board that the Arduino company sells. It's called the Arduino Uno. The Arduino Uno has an embedded Atmega 328P microcontroller, which is responsible for storing and executing programs. It is the large component found below the Arduino logo on the board. What the programs it runs do is entirely up to you, but fundamentally, all actions are carried out through interactions between the pins on the microcontroller and other electronic devices. When we talk about pins in this workshop, we will be referring to the black rails on the top and bottom of the board, which you can insert wires into. Although these are not the same as the pins on the microcontroller, their purpose is to allow you to interface with the microcontroller, so we will focus on them rather than the microcontroller's actual pins. So what can you do with an Arduino board such as an Arduino Uno? These boards can control a wide variety of hardware since they're capable of voltage sensing, outputting signals, and communication using many different protocols, all of which is directed by the microcontroller based on how you've programmed it. One thing you can use an Arduino board for is to control a custom-built device to perform a specific task. For example, a common Arduino project is to create a miniature robotic arm using some structural material and servos for movement. And then the Arduino board can send control signals to the servos to change the position of the arm based on signals that the user sends to the Arduino, or based on algorithms running on the Arduino for automatic control. You can also interface the Arduino with existing hardware to use it in new ways. For example, the wires from a video game controller can be connected to the Arduino pins in order to receive data from the sensors in the controller, which allow it to determine which buttons are pressed or where the joysticks are positioned. This data can be used to create a certain output from the Arduino board when a certain action is performed with the controller, such as pressing a button, and then that output can control any other device that can interface with an Arduino board. So this allows you to control that other device with the video game controller, even if that wouldn't be possible normally. The best way to see what's possible with Arduino is to look for yourself by going to the project hub, which is a public forum for people to share Arduino projects. I have a link to the project hub on this slide. So I also want to mention how we at UCR-UAS have used Arduino in our project. Primarily, we've been using it for our automation and data collection purposes. So since the vehicles we design at UCR-UAS use a large number of actuators and sensors, the ability of Arduino boards to interface with many of these devices at once, it's very valuable to us. And we have uses for Arduino boards in both of the vehicles that we're creating and in other places as well. In some cases, there's not enough room to fit a full Arduino Uno. Fortunately, there are smaller Arduino boards we can use that do many of the same things. So let's focus on how Arduino is used in the creation of the Unmanned Ground Vehicle, or UGV, which is integrated into the mission that our UAV must carry out. So the UGV is a small ground vehicle which is initially stored inside of the UAV, and when the UAV reaches a certain point, it is deployed and drops to the ground. After the UGV reaches the ground, it needs to navigate to a target location autonomously. An Arduino board can be used to enable this autonomous movement by interfacing with the motors that move the UGV, as well as the sensors on board which provide telemetry information. The same system can be used for manual movement, but in that case, the Arduino is responding only to external commands rather than determining the correct control signals on its own. So the first use of the Arduino board actually takes place before the UGV even reaches the ground. The UGV is deployed at an altitude of around 100 feet, which means that letting it free fall to the ground isn't an option. Fortunately, a parachute can be used to limit the velocity of the UGV until it gets to a safe altitude, which in this case is 5 feet. As you can see in the diagram on the right here, the UGV starts out falling, but there's a parachute attached to it that is deployed automatically just by the air pressure, and it will continue to fall with the parachute on until it reaches an altitude of 5 feet, and at that point, the parachute is discarded so that it doesn't get in the way of the UGV when it starts moving. Now, we can develop an altitude detection system using the Arduino board to automatically detach the parachute. The Arduino itself doesn't have a way to detect altitude, so we introduce a sensor called an altimeter, shown here in the middle image. And that detects the altitude every few milliseconds and sends the information to the Arduino board. When the altimeter reports an altitude less than 5 feet, the Arduino is programmed to rotate a servo in order to detach the parachute. The diagram on the bottom left here summarizes the interaction, showing how the Arduino takes information from a single source, the altimeter, and uses it to determine how to control an actuator. Next, we will cover an example where the Arduino must use information from multiple sources to determine how it controls actuators. For the main mission of the UGV, the vehicle will need to travel to different points, but there needs to be a source for the control signals applied to the motors, which control the wheels on the UGV. Once again, the Arduino board is the solution. The program running on the board includes algorithms which can use the motors to turn the UGV or drive it forwards. However, the Arduino board has no sense of direction on its own, nor is it aware of the location of the UGV relative to the destination. So again, sensors are introduced to provide that information. The GPS coordinates of the destination are already known and can be used along with the GPS coordinates of the UGV itself to determine the correct orientation. A GPS onboard the UGV gives the Arduino an up-to-date set of GPS coordinates for the UGV, allowing the coordinates to be compared in real time. To detect the current orientation of the UGV, a second sensor called a compass is used. The algorithms used by the Arduino consider the information from both sensors at once to determine the correct course of action. And we have images of the GPS module that is used on the UGV, as well as the compass. Now, if you look in the top right, that we have an example scenario where the UGV, represented by the cylinder, is currently facing towards the top of the slide, as shown by the black arrow. But the destination, marked with a capital letter A, is located some distance to the right at a 45-degree angle to the direction the UGV is facing. Given this information, which could be determined by comparing the GPS coordinates to get a vector from the UGV's location to the destination, and then finding an angle between that vector and the direction the UGV is facing. The Arduino will slow down the vehicle if needed, and then turn it 45 degrees clockwise before moving forwards. The Arduino will then monitor the distance between the GPS coordinates until the UGV is close enough to start slowing down. Now that we've explained the motivation for learning Arduino programming, let's take a quick look at the major topics we will be covering in this workshop series. So first, you will learn the structure of an Arduino program and how to adapt to it. That will be the main focus of this session. After that, you will learn how to interact with multiple circuit components at once using the Arduino board. Then you'll learn how to use serial communication to communicate data between a computer and an Arduino board. After that, you'll learn how to interact with important hardware like sensors and servo motors. Next, you'll learn how to use an external display to present information. And then finally, you'll create a game that puts together many of the Arduino concepts that you learn over the course of these workshops as sort of a capstone project. And you'll be able to learn many other useful tidbits during these workshops as well. So with that in mind, let's start with the first topic of discussion for this session, which is the major differences between Arduino programming and general C++ programming. I will not be able to give a comprehensive list of the differences, but I will be sharing the most important ones in order to prepare you for the programs that you will be seeing during this workshop series. The main aspect of programming an Arduino board that separates it from general C++ programming is the need to interact with pins on the board. In an Arduino program, digital input and output pins are referred to by a number, while analog pins are referred to by the capital letter A followed by a number. And you can see on the board that the pins are labeled by their number, and you will use the same number to refer to them in a program. Now, the programming language for programming Arduino boards contains certain built-in functions to allow these pins to be used. Examples include the pin mode, digital read, and digital write functions. If you look at the arguments that these functions take in, you can tell that they're going to be acting on specific pins. So to learn more about the built-in functions that the Arduino programming language offers, you can visit the official documentation on the Arduino website. I have a link to that on this slide. Other than having a single main function, most Arduino programs use two functions, setup and loop. These functions are called automatically when running the program, much like the main function is called automatically upon starting a C++ program. The setup function is the first function which the program enters, and it is executed to completion only once. Once the setup function ends, the program jumps to the loop function. However, once the loop function has been executed to completion, the program returns to the beginning of the loop function and executes it again. And this will continue until the Arduino board is reset, which can be done by pressing the button on the board, opening a connection to it from your computer, or unplugging it from its power source. As a consequence of this program structure, we need to rely much more on global variables than we would in a general C++ program. This is because we will often need to initialize variables or objects in the setup function so that they can be used in the loop function, and they will need to retain their values when moving between the setup and loop functions or between iterations of the loop function. Variables which are only used temporarily during a single execution of a function can still be declared locally, and this is typically more memory efficient than making them global variables. And I have an image on this slide that hopefully shows you the difference between a local variable and a global variable. The global variable is declared outside of any functions, whereas the local variable is declared, in this case, inside the setup function. And so from the perspective of the program, it only exists while you're in the setup function. So getting an Arduino board to run your program is a two-step process. The first step is to compile the program into machine code, much like you would any C++ program. The second step is to upload the machine code to the microcontroller on the Arduino board in a process called flashing the microcontroller. The Arduino board will immediately begin running a program once it has been flashed. And to give you a better idea of the process involved, I'm going to pull up the Arduino development environment. So you should be able to see the Arduino IDE on the screen now. I've pulled up an empty sketch, which a sketch is just another name for an Arduino program. If you look in the top left corner, you'll see these two buttons. The one with the check mark is the verify button. The one with the arrow is the upload button. The verify button will just compile your code. So if you just need to check whether your code will compile without uploading it, that's the button you would use. If you do want to upload your code, you would use the upload button, which will both compile your code and then upload it to a board if there's one connected to your computer. So I'm going to show you what happens when I compile this sketch. You see it usually takes a bit of time. And then once it finishes, it actually gives you a summary here of how much of the microcontroller's memory the program would occupy if you uploaded it to the board. Now I can also show you what happens if I try to upload, but since there's no Arduino board connected to my computer, it's going to throw an error. But you saw right after I clicked the button, it actually compiled the program again. So even though I had just used the verify button, it's still going to automatically compile the code. So this is a process you'll have to repeat every time you need to test your code on a physical Arduino board. But for this workshop, most, if not all of us, are going to be working in Tinkercad using a simulated Arduino board rather than on a physical Arduino board. And the steps to go through in that case are a bit different. So I'm going to take a look at that right now. So Tinkercad uses a simulated environment in which each Arduino board has a different set of code associated with it. A simulated board runs its code from the beginning each time the simulation is started. When the start simulation button is pressed, all code will first be compiled, and the simulation will only start if there were no errors found by the compiler. And then to reset your Arduino board, you have to stop the simulation and start it over again. Another thing to consider when using the simulated environment provided by Tinkercad is that hardware will not always be able to function in a way that matches real life. So to show you what I mean, I'm going to bring up a pre-made Tinkercad workspace. So this is what the Tinkercad workspace looks like. If you look on the right-hand side, there's the list of components you can drag and drop into the workspace. Above that is the Start Simulation button, as well as the button to see the code that is associated with your simulated Arduino board. Right now, I want us to focus on this right here. What we have here is called a photoresistor, which we'll be talking about more in a later session. All you need to know right now is that a photoresistor in real life will react to the level of light which it is exposed to by changing its resistance. In Tinkercad, this is not determined by proximity to actual light sources like it would be in real life, but rather the stimulus that the photoresistor responds to needs to be set manually. So if I start the simulation, I have a multimeter that is currently measuring the resistance across this photoresistor. Right now it's reading 180 kiloohms or 180,000 ohms, and we use this resistance to determine the reading of the photoresistor. So if I click on the photoresistor, then they get this slider that pops up, and the amount of light that the photoresistor will behave as if it is exposed to will depend on where I move the large black circle on the slider. When I have the circle on the left side, or the right side, then the photoresistor behaves as if there's no light being exposed to it. But as I move the slider to the left, you see the resistance went down. At first it was 180,000 ohms, but if I slide it all the way to the right, now it's only 506 ohms. So the photoresistor is behaving as if it's being exposed to an increasing amount of light. And photoresistors are not the only sensor that acts like this. So when you're going to be testing projects that make use of sensors in Tinkercad, you have to keep this in mind. It might not be as realistic as a real life sensor. Now, another piece of hardware that I want to take a look at is the servo motor. We'll also be covering this in a future session. You can see that the position of the servo is indicated by the angle of the cross-shaped servo arm. In this case, the servo looks like it is moving very slowly, but this is partly due to the fact that the simulation is running much slower than real time. If you look at this top ribbon, you can find a count of how much time has passed since the simulation has started. It's called simulator time. And if this is counting much more slowly than time passes in real life, that means there's some lag in the simulation. And as a result, things will look like they're moving more slowly than they really are. Now, unfortunately, there's no way to change the speed of the servo itself. So if you want to make sure that a servo actually reaches a certain position, you need to account for its speed to ensure that it reaches that position before the next instruction is sent to it from the Arduino board. So I want to make sure everyone is taking this information taking this information in all right. So if you have any questions, feel free to put them in the chat. All right, I'm not seeing any questions right now. So for now, I'll move forward with the presentation. So in order to better introduce the basic concepts in using an Arduino board, let's work through a simple example where a button is used to control a single LED. For those who are not familiar with the terminology, an LED, or light-emitting diode, is a basic 2-pin circuit element which dissipates power while emitting light, but only if it's able to conduct current in a specific direction. The LED must have one pin called the anode, held at a higher voltage than the other pin called the cathode in order to conduct current. For those of you who have taken Physics 40C or a basic EE class, you know that power is dissipated when current flows from a higher voltage to a lower voltage. So in this case, current must flow from the anode to the cathode for the LED to emit light. One way to ensure that current flows through the LED in the correct direction is to have the cathode connected to the ground and apply a positive voltage to the anode, which will necessarily cause the anode to have the higher voltage. On the other hand, if the anode has a voltage of 0 volts, then the voltage difference will be negligible and then no current will flow. By the way, I know I'm starting to talk a lot about voltages right now, which may be confusing to some of you, but I'm mainly giving it as a background information to explain why the circuit we'll be looking at behaves like it does. So you don't necessarily need to understand everything I say about voltages here to learn how to use Arduino in these workshops, and we'll be less focused on these details in future sessions. So in this case, the Arduino board is going to be acting as an intermediary between the button and the LED. So rather than having the button directly control current through the LED, the Arduino board will determine the state of the button and then send the appropriate control signal to the LED based on that state. So the first thing we need to be able to do is determine whether the button is being pressed. To see how we can do that, let's take a look inside the button that we'll be using. So we're going to be using a 4-terminal button like the one pictured in the image on the left. I think I got the direction wrong. Again, it's the right side. And this image, or no, I meant the left side of the image is on the right. So this one, the one in color, this image shows the exterior view of a 4-terminal button, and its terminal has the terminals labeled A through D. We can see that terminals A and C are on the same side of the button as our terminals B and D. The picture on the right shows how the terminals are connected inside of the button. So we can see that terminals A and B are always connected, and so are terminals C and D. So the break in the line in between these pairs of terminals indicates that the connection is controlled by a switch. So when the button is up, there's no connection in the middle, and when the button is down, there is a connection. This means that when the button is pressed, all 4 of the terminals will be connected for as long as the button is held down. This suggests that we can use the voltage on one of the button's pins to determine whether the button is up or down. In this case, let's use terminal B. So if terminal D is grounded, that means it's at 0 volts, and also anything it's connected to is at 0 volts. So terminal C would also be at 0 volts. And then if we also apply a positive voltage to terminal A, then and when the button is up, this positive voltage will also be experienced by terminal B because it's always connected to terminal A. But we will know that the button has been pressed if terminal B begins to have 0 volts, because that will only happen if the connection in the middle is present, which will allow terminals A and B to be grounded through terminal D. So I'll show you how this applies to the actual circuit we're going to be analyzing, also in Tinkercad. So this is the completed circuit. We're going to be focusing on the button here right now. So if you recall how the terminals were labeled in the slides, the terminal connected to the red wire will be terminal A, the terminal connected to the orange wire would be terminal B, and the terminal connected to the black wire would be terminal D. So terminal B is connected to digital pin 2 on the Arduino board. So this means we can use digital pin 2 to detect the voltage on terminal B, since the wire will mean they have the same voltage. And terminal A is connected through this red wire, which has a 1 kilo ohm or 1000 ohm resistor, down to the 5-volt output pin on the Arduino. So, and the 5-volt output pin just outputs a constant 5 volts, which means that up to this resistor it is at 5 volts. Then the resistor is going to have some voltage drop across it. That depends on how much current is flowing through it. And then the voltage minus that voltage drop is what goes in, is seen at terminal A. So first, let's see what happens when the button is up. So terminals A and B are connected, but they're not connected to any of the other terminals. And this gives one complete path for current to take. So the current comes out of the 5-volt pin, travels along the red wire, going through the 1 kilo ohm resistor. Then it travels through the button in through terminal A, out through terminal B. And it travels into digital pin 2. Because digital pin 2 is an input pin, it will, after passing through it, it'll go through a very large internal resistance. After that, it'll end up at the ground inside of the Arduino. And so the current travels through 2 resistances, the resistor on the red wire and the internal resistance at digital pin 2. And when 2 resistances are in series, like this, where the same current flows through both of them, then the proportion of the overall voltage drop that each individual resistance is responsible for will depend on how much larger or smaller it is compared to the other resistance. In this case, the overall voltage drop is 5 volts, and the internal resistance is responsible for most of that because it is far larger than the 1 kilo ohm resistor. As a result, the voltage that is seen at pin 2, it is equal to the voltage drop across that internal resistance. So it's going to be close enough to 5 volts for it to be considered a high voltage, which means that if I call digital read on pin 2, when there's that signal applied to it, then it's going to return true. That means it's because it returns true when it's reading a high voltage. We'll look at how that works in the code later. Now, let's say what happens if the button is pressed down. Well, then we're going to have the internal connection between terminals A and B and terminal D. Terminal D is connected through this black wire directly to the ground on the Arduino. And that is the same ground that the current gets to when it goes through digital pin 2. So basically now there's 2 paths that current can take to get to the ground. It can either, once it reaches terminal A, it can either pass through the the orange wire into digital pin 2 and through that internal resistance, or it can pass through the black wire and into the ground pin where there is no resistance. So because current will always take the path of least resistance, all the current in this circuit is going to flow in terminal A and out terminal D. So as a result, there's going to be no voltage drop in the internal resistance, which means there will be 0 volts at digital pin 2. We also have 0 volts on terminals A and B because if they're being connected to the ground. And you might be wondering how it is that terminal A could be at 0 volts when it's being connected to the 5-volt pin on the Arduino. The reason for that is that once the button is down, all the voltage drop will happen across this 1 kilo ohm resistor. So that explains how we're going to use the voltage on terminal B to figure out whether the button is up or down. Now, one thing I want to mention is the resistor on the red wire. If you're wondering why we need to have such a high resistor there, especially since there's already an internal resistance at digital pin 2, the purpose of this resistor is to prevent short circuits when the button is down, because we just saw that terminal A is connected to the 5-volt output pin on the Arduino board. If the resistor wasn't there, then it would just be a direct connection, which would mean that there's no voltage drop in between. And so if terminal A is connected to terminal D, which is grounded under that scenario, then the 5-volt output on the Arduino board would try to supply the current that's needed to maintain a voltage of 5 volts on terminal A, despite the fact that the ground pin being connected to terminal A is forcing it to have a voltage of 0 volts. And as a result, you would end up with a dangerous level of current coming out of the 5-volt output and then going directly to the ground from there. When you have a voltage source connected directly to the ground, that is considered a short circuit. But so long as you have a resistor somewhere along that path that has a high enough resistance to prevent the current from exceeding safe levels, then it won't be a problem to create a connection like that. So in summary, we can use digital read on digital pin 2 to get the voltage level at terminal B. Digital read will return false or 0 if the voltage is low or 0 volts, and it will return true or 1 if the voltage is approximately 5 volts. And then we'll use that Boolean value to determine whether the button is up or down. So a Boolean value of false here would mean that the button is down because it means terminal B is connected to terminal D, and Boolean value of true will mean that the button is up because in that case terminal B is only connected to terminal A. So now that we know how the Arduino board is going to actually, let's we need to talk about the LED here. So as mentioned before, we connect the cathode to the ground pin, and we're actually going to have a resistor between them. It fills the same purpose as the resistor on the red wire. So it's limiting the current that flows through when the LED is on, because even though the LED provides some resistance on its own, it's not enough to keep the current at a safe level. And digital pin 7 is connected to the anode of the LED. So we'll have pin 7 be an output pin so that we can control its voltage. We can use digital write to either set its voltage to 0 volts, which is low voltage, or 5 volts, which is high voltage. And when we want the LED to be off, we will set it to 0 volts. When we want the LED to be on, we will set to 5 volts. So now we can see what the code to implement this control looks like. So we're going to have a setup function and a loop function. And in the setup function, we're simply going to use the pin mode function to specify which digital pin is an input pin and which is an output pin. In the loop function, we're going to check the status of the button, and depending on that status, either hold the LED on or off. We know from before that if digital read on pin 2 returns false, then the button is down. We can take the logical inverse of the Boolean value returned by digital read. We denote the logical inverse using an exclamation mark, and it's going to convert a true into false and false into true. So this way, if we get true, then we know the button is down. So let's look at how the code looks in Tinkercad. So in the setup function, we just have the 2 pin mode functions. So to set digital pin 7 as an output, we just need to use the number 7 as the first argument and then for the second argument, type output in all caps. We do a similar thing for digital pin 2, except we're specifying it as an input pin, so we type input in all caps. Now, the loop function is what's going to be running while we have the simulation going on. It's going to keep running through the loop function. And in this case, we just have a single if-else statement. So for those unfamiliar with if-else statements, there will always be a Boolean statement that can evaluate to either true or false, which goes in the parentheses after the word if. And when it evaluates to true, the code in the first section will execute, starting with the line right below if. In this case, there's only one line. However, if the statement evaluates to false, then the code in the second section following the word else will execute instead. So the conditional statement that's being evaluated is the logical inverse of digital read on pin 2. Just like we said, if that returns true, then the button is down. If that returns false, then the button is up. So, and we already know when the button is down, we want to set 5 volts on digital pin 7. So we call the digital write function. We pass in the number 7 as the first argument, and then the word high in all caps to specify we want a high voltage. On the other hand, when the logical inverse of digital read on pin 2 returns false, then the button is up, and we want to make sure that the LED is off. So we use digital write on pin 7 again, but this time say low for low voltage. So this way, it will be continuously running through this if-else statement, and as soon as the state of the button changes, then it will change which one of these digital write functions that gets executed. So the LED will respond very quickly because this code is executed many times every second. So let's actually verify that this code works by running the simulation. So you can see when I'm not touching the button, the LED is off. So we know it's correctly executing the part in the else part of the if-else statement. When I click on the button, the LED turns on, and so it's switched to executing the part under the if. Then as soon as I let go, the LED turns off again, as expected. So there you have it. That is our first Arduino circuit. I know that even though this was a simple example, there was a large number of concepts involved. So if you have any questions, feel free to ask them during the office hours that I'll be having right after the workshop. They're going to be in this same Zoom meeting, so you can just stay right here. And now I'll just briefly cover some things to do before our next session, which will be on Tuesday of next week, so April 13th at 4:00 p.m. So a slightly different time than most of the workshops in this series. And that session will actually be taught by Sahas, was the computer science team lead at UCR-UAS, and he was also one of the instructors for our last workshop series. Before that session, you should install the Arduino IDE and get a Tinkercad account if you haven't already. If you need instructions on how to do this, you can find them on the GitHub repository for these workshops, which you can get to by following the link on this slide. I recommend you familiarize yourself with the GitHub repository now, because we'll be using it to release practice exercises starting next session, which will be good for letting you practice the skills you learn during these workshops. And finally, make sure you understand the basic functions for interacting with digital pins. Those are the pin mode, digital write, and digital read functions that we just covered, because they'll continue to be used in future sessions. So to understand what's going on when we get there, you'll want to make sure you understand the basics of how those functions work. So if you feel like you don't quite understand it yet, please stay for office hours, and I'll try to help you out with that. So thanks everyone for coming. That's all for today. I guess we can, if there's any other announcements that need to be made, if Train can say them now, otherwise we can get into office hours.
Yeah, thanks everyone for coming. So I've posted links into the chat. Remember, we have a general meeting this Friday at 5 p.m. So check out our website for more information, Zoom link and all that stuff. And I hope to see you guys there. And I hope to see you guys next week for session 1. Thank you.